Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. As humanity enters the mid-2020s, our planet faces unprecedented challenges. Rising sea levels threaten coastal cities worldwide, with projections suggesting up to 2 meters of increase by the end of this century. Meanwhile, our population continues to grow, expected to reach nearly 10 billion by 2050. Urban centers already house 55% of all humans, a figure projected to reach 70% within 3 decades. The math is simple and sobering. We need more space. This convergence of challenges has sparked renewed interest in a frontier that has fascinated humanity for centuries, the underwater realm. The concept of underwater habitation isn't new. Jacques Cousteau's Health projects in the 1960s demonstrated that humans could live beneath the waves for extended periods. What is new is the technological capability and growing necessity to establish permanent underwater settlements, not just for research or novelty, but as functional extensions of our civilization. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe, it's free, and it helps us grow this community together. The oceans cover 71% of Earth's surface, yet we've explored less than 20% of their depths. This vast, largely untapped frontier offers potential solutions to multiple crises: living space, resource scarcity, and even climate resilience. Underwater habitats could function as self-contained ecosystems, utilizing resources from their surroundings while minimizing environmental impact on both aquatic and terrestrial environments. Currently, underwater facilities exist primarily as research stations, oil platforms, and military installations. The Aquarius Reef Base off the Florida Keys operates at a depth of 62 feet, allowing scientists to conduct extended research missions without daily decompression. China's Hainan Deep Sea Center supports underwater operations at significantly greater depths. These examples, while impressive, represent only the earliest prototypes of what could become fully functional underwater cities. The transition from temporary habitats to permanent settlements requires overcoming formidable challenges. Water exerts approximately 1 atmosphere of additional pressure for every 33 feet of depth. At just 100 feet down, structures must withstand 4 times the pressure experienced at sea level. This fundamental reality shapes every aspect of underwater construction, from material selection to architectural design. Beyond pressure concerns, underwater habitats must contend with corrosion from saltwater, biofouling from marine organisms, and the constant threat of leaks. Energy generation, waste management, and food production all require rethinking when divorced from terrestrial infrastructure. Perhaps most challenging is the psychological impact of living in an environment where the nearest breath of fresh air might be hundreds of feet away. Yet these challenges have inspired innovative solutions across multiple disciplines. Advanced materials like carbon fiber reinforced polymers offer unprecedented strength-to-weight ratios. Closed-loop life support systems, originally developed for space exploration, can be adapted for underwater use. Aquaculture and hydroponic techniques provide sustainable food sources. Most importantly, developments in renewable energy, particularly ocean thermal energy conversion, wave power, and advanced nuclear technologies, could provide the consistent, high-density power these settlements would require. As we stand at this technological crossroads, underwater habitation represents more than a solution to immediate problems. It offers humanity a new frontier, one that might reshape our relationship with the planet we call home. In the parts that follow, we'll explore the specific engineering challenges and promising opportunities that underwater cities present, examining how these subaquatic settlements might transform from science fiction to reality within our lifetimes. The fundamental challenge of underwater construction begins with a simple question: how do you build structures that can withstand enormous external pressure while remaining habitable for humans who evolved in a 1-atmosphere environment? This question drives the structural engineering of underwater habitats, and shapes everything from material selection to architectural geometry. Conventional construction materials like concrete and steel face significant limitations underwater. While concrete offers excellent compressive strength, traditional formulations deteriorate rapidly in saltwater environments. Steel provides necessary tensile strength but faces accelerated corrosion when exposed to seawater. These challenges have spurred development of specialized materials, including ultra-high-performance concrete formulations with silica fume and superplasticizers that achieve compressive strengths exceeding 20,000 pounds per square inch. 5 times stronger than conventional concrete. Fiber-reinforced polymers, FRPs, represent another promising material category, offering excellent strength-to-weight ratios and inherent corrosion resistance. Carbon fiber composites, while expensive, provide tensile strengths up to 7 times that of steel, while weighing substantially less. Glass-reinforced polymers offer more economical alternatives with moderate performance characteristics. Recent advances in material science have produced graphene-enhanced composites that may eventually surpass all existing options in terms of strength, weight, and durability. Architectural geometry plays an equally crucial role in underwater structural design. Spherical forms distribute pressure loads evenly, but present manufacturing challenges. Cylindrical structures offer easier construction while still providing reasonable pressure distribution. The most promising designs combine multiple geometric forms, typically spherical living spaces, connected by cylindrical corridors, to optimize both structural integrity and functional space. Biomimicry offers additional design inspiration. Marine organisms like deep-sea sponges and diatoms have evolved intricate skeletal structures that provide remarkable strength despite minimal material use. Researchers at MIT and the University of California, San Diego have developed computational models that apply these biological design principles to architectural forms, potentially reducing material requirements by 30 to 40% while maintaining structural integrity. The depth of placement fundamentally determines design requirements. Shallow underwater structures, those at depths less than 100 feet, face significantly different challenges than those at greater depths. Shallow habitats may employ positive buoyancy designs, where the structure's natural tendency to float is countered by anchoring systems. This approach minimizes compression forces on the habitat itself, but requires robust mooring systems that can withstand strong currents and storm events. Deep habitats, conversely, typically employ negative buoyancy designs, resting on the seafloor. These structures must withstand the full hydrostatic pressure at their deployment depth and are typically heavier and more robust in construction. The intermediate zone, between approximately 100 and 300 feet, represents a particularly challenging design space where structures must balance buoyancy considerations with pressure resistance while remaining within the range of conventional diving operations for maintenance and emergency access. Construction methodologies present their own unique challenges. Traditional scaffolding approaches used in terrestrial construction prove impractical underwater. Instead, underwater habitats typically employ modular construction techniques where components are fabricated on land, transported to the site, and assembled underwater by specialized equipment or saturation divers. Recent developments in underwater 3D printing technology may eventually allow on-site fabrication of structural components, potentially revolutionizing underwater construction techniques. Connection points between modules represent critical vulnerability zones, requiring specialized engineering attention. These junctions must maintain watertight integrity while accommodating slight movements caused by currents, temperature variations, and even seismic activity. Advanced gasket materials incorporating self-healing polymers show promise for addressing these challenges, potentially sealing minor breaches automatically before they become catastrophic failures. Creating a habitable environment beneath the waves represents an extraordinary life support challenge comparable to space habitation. Both environments are immediately lethal to unprotected humans, requiring comprehensive environmental control systems to sustain life. These systems must address 5 critical functions: atmosphere management, water processing, waste handling, temperature regulation, and emergency response capabilities. Atmospheric management begins with maintaining breathable air composition. Humans require oxygen concentrations between 19 and 23% to function optimally, while carbon dioxide must remain below 0.5% to prevent hypercarbia symptoms. Underwater habitats typically maintain internal pressure at or slightly above surface atmospheric pressure to prevent water infiltration. This creates a complex balance. Higher internal pressure increases nitrogen saturation in inhabitants' tissues, potentially causing decompression sickness during evacuation scenarios. Modern atmospheric management systems employ regenerative processes rather than simple gas storage. Electrochemical carbon dioxide scrubbers extract CO2 from habitat air, concentrate it, and either sequester it or repurpose it for other uses, such as algae cultivation. Oxygen generation typically occurs through either electrolysis of water, splitting H2O molecules into hydrogen and oxygen, or chemical oxygen generators that release oxygen through controlled reactions. Both approaches require significant energy input, making atmospheric management one of the most power-intensive life support functions. Water management presents different challenges. While surrounded by water, underwater habitats cannot simply use their surrounding medium. Seawater contains approximately 35 grams of salt per liter, making it unsuitable for drinking or most technical applications. Desalination systems, typically employing reverse osmosis or vacuum distillation, must produce fresh water for drinking, hygiene, and various habitat operations. Wastewater must undergo treatment before discharge to prevent environmental contamination and avoid attracting marine life to habitat structures. Waste management systems in underwater habitats must operate with near-perfect efficiency, as storage space for solid waste remains extremely limited. Biological waste treatment systems, mimicking terrestrial sewage processing, can break down organic wastes, but require careful design to function in the confined space of an underwater habitat. Anaerobic digestion systems offer promising alternatives, breaking down organic waste while producing methane that can supplement habitat energy supplies. Temperature regulation represents another continuous challenge. Water conducts heat approximately 25 times more efficiently than air, making underwater habitats prone to rapid heat loss without proper insulation. Conversely, the electronic systems required for habitat operation generate significant waste heat that must be dissipated. Advanced thermal management systems typically employ both active and passive approaches. Multi-layer insulation protects against conductive losses, while liquid cooling loops transfer excess heat either to habitat water systems or directly to the surrounding ocean. Environmental monitoring technologies serve as the nervous system of life support operations. Modern systems employ redundant sensor networks, measuring dozens of atmospheric, water quality, and structural parameters. Machine learning algorithms analyze these data streams to identify potential problems before they become critical, allowing for preventative maintenance rather than emergency response. Quantum sensor technologies currently under development promise significant improvements in sensitivity and reliability, potentially detecting minute environmental changes or structural stresses long before they would register on conventional systems. Emergency response capabilities form the final critical component of life support design. Multiple redundant systems, typically operating on independent power supplies, stand ready to activate during system failures. Emergency oxygen supplies, typically using chemical oxygen generators, can maintain breathable atmospheres for 72 to 96 hours during primary system outages. Pressure equalization systems can stabilize habitats during breach events, while emergency positive buoyancy systems can bring damaged habitat sections to the surface when necessary. The integration of these systems creates challenges beyond their individual complexity. Life support components must communicate seamlessly, prioritizing critical functions during power limitations and coordinating responses during emergency scenarios. This system of systems approach mirrors developments in smart building technology, But with far higher stakes, a failure in an underwater habitat's environmental control systems could prove catastrophic within minutes. Powering underwater habitats presents unique challenges and opportunities. Unlike terrestrial structures that can connect to established electrical grids, underwater facilities must generate sufficient power independently while operating in one of Earth's most challenging environments. This constraint has driven innovative approaches to energy generation, storage, and management specifically adapted to the subaquatic realm. The energy demands of underwater habitats significantly exceed those of comparable surface structures. Life support systems operate continuously, pressurization equipment consumes substantial power, and artificial lighting replaces natural sunlight. Preliminary estimates suggest that a habitat supporting 100 inhabitants might require between 2 and 5 megawatts of continuous power, comparable to the needs of a small terrestrial town, but concentrated in a much smaller space. Surface-tethered power delivery offers the most straightforward approach for shallow habitats. High-voltage direct current, HVDC transmission lines, can deliver power from shore-based generation facilities with approximately 5 to 8% transmission losses per 100 kilometers. This approach provides reliable power but creates strategic vulnerabilities. Damage to the power cable could jeopardize the entire habitat. Most designs incorporating surface tethering include substantial backup generation capacity to mitigate this risk. Ocean thermal energy conversion, OTC, represents one of the most promising indigenous power generation technologies for underwater habitats. This approach exploits temperature differentials between warm surface waters and cooler deep waters to drive turbine systems. Traditional OTEC designs achieve modest efficiency, typically 5 to 7%, but recent closed-cycle systems, incorporating advanced working fluids, have demonstrated efficiencies approaching 15%. A single 100-megawatt OTEC plant could theoretically power multiple underwater habitats while producing desalinated water as a beneficial byproduct. Current energy harvesting technologies offer complementary power sources. Advanced designs can extract energy from natural underwater currents, converting kinetic energy to electricity with efficiencies approaching 40%. Wave energy converters positioned near the surface can generate substantial power from ocean swells, with fifth-generation devices achieving capacity factors exceeding 35% in appropriate locations. These technologies offer particular advantages for habitats positioned near continental shelves, where currents tend to be strongest. Nuclear power systems provide high energy density and reliability, critical for deep underwater applications where surface tethering becomes impractical. Small modular reactors, SMRs designed specifically for underwater deployment, could provide 50 to 300 megawatts of continuous power for decades without refueling. Emerging designs emphasize passive safety features and sealed reactor vessels to minimize operational risks in underwater environments. Thorium-based reactor designs offer potential advantages through reduced waste production and elimination of weapons-grade byproducts. Energy storage remains essential for all underwater power systems, providing resilience against generation fluctuations and emergency backup capacity. Advanced battery technologies, including lithium titanate systems, offer promising characteristics for underwater applications, including rapid charging capabilities, long cycle life exceeding 20,000 cycles, and improved safety profiles compared to conventional lithium-ion designs. Emerging metal-air battery technologies may eventually provide energy densities approaching those of fossil fuels, while using abundant materials compatible with underwater environments. Compressed air energy storage, CAES, offers another compelling approach uniquely suited to pressurized underwater environments. These systems compress air during excess power availability and release it through turbines when additional generation is needed. The natural pressure differential between habitat interiors and the surrounding water can significantly improve system efficiency compared to terrestrial CAES installations, potentially achieving round-trip efficiencies exceeding 70%. Power distribution within underwater habitats requires specialized approaches to ensure safety and reliability. Superconducting power cables, operating at the naturally cold temperatures found in deep water, could eventually enable essentially lossless power transmission between underwater facilities. In the nearer term, medium-voltage DC distribution systems offer significant efficiency advantages while minimizing electromagnetic interference with sensitive communication and life support electronics. Ultimately, underwater habitats will likely employ hybrid energy systems combining multiple generation and storage technologies to ensure reliability while optimizing efficiency. Artificial intelligence-driven power management systems will continuously balance generation sources, storage reserves, and consumption patterns, potentially trading power with neighboring habitats through underwater microgrids to further enhance system resilience. Maintaining reliable communication links between underwater habitats and the surface world represents one of the most challenging aspects of subaquatic settlement development. Water, particularly salt water, severely attenuates electromagnetic signals, rendering conventional radio communication essentially useless beyond shallow depths. This fundamental physical constraint has driven development of specialized systems for underwater data transmission that combine multiple technologies operating across different physical principles. Acoustic communication represents the most mature technology for underwater data transmission. Sound waves propagate effectively through water, traveling approximately 4.5 times faster than in air. Modern acoustic modem systems can achieve data rates up to 30 kilobits per second, over distances reaching several kilometers. Advanced systems employing sophisticated signal processing algorithms can partially overcome challenges like multipath propagation, where sound waves reflect off the surface, seafloor, and underwater structures, creating interference patterns. Despite continuous improvement, acoustic communications suffer from fundamental limitations. Available bandwidth remains severely constrained compared to terrestrial systems, and latency, the time delay in signal transmission, can be significant over longer distances. These constraints make acoustic systems suitable for telemetry, text communication, and low-resolution imagery, but inadequate for high-definition video conferencing or large data transfers that modern communications increasingly require. Optical communication systems offer dramatically higher bandwidth, with experimental laser-based systems demonstrating data rates exceeding 1 gigabit per second. However, suspended particles in water scatter and absorb light, limiting effective range to approximately 100 meters in even the clearest ocean conditions. This constraint has led to the development of hybrid systems where short-range, high-bandwidth optical links connect to acoustic systems for longer distance transmission, effectively creating underwater communication cells analogous to terrestrial mobile phone networks. Tethered communication offers the most reliable high bandwidth option for underwater facilities. Fiber optic cables can deliver essentially unlimited bandwidth with minimal latency, enabling everything from real-time video conferencing to complex scientific data transmission. The Japan Agency for Marine Earth Science and Technology, JAMSTEC, demonstrated this capability with their advanced seafloor observation network, which uses fiber optic cables to transmit multiple high-definition video streams from depths exceeding 2,000 meters. Physical cable systems, however, create vulnerability points and maintenance challenges. Underwater cables must withstand enormous pressure, resist corrosion, and avoid damage from marine life and geological activity. Redundant pathways and self-healing network architectures help mitigate these risks. Recent developments in underwater-specific cable designs incorporate protective metallic sheaths, hydrogen-resistant fiber formulations, and flexible articulation points to accommodate seabed movement during seismic events. For deeper habitats, where surface tethering becomes impractical, a promising approach involves underwater communication buoys that serve as relay stations between submerged habitats and surface or satellite networks. These autonomous platforms can incorporate multiple communication technologies, acoustic systems for underwater connections, and conventional radio or satellite links for surface communication. Solar panels and wave energy converters provide power, allowing indefinite deployment periods with minimal maintenance requirements. Within underwater habitats themselves, conventional electromagnetic communications function normally in the air-filled environment. However, special considerations apply to network design, including enhanced electromagnetic shielding to prevent interference with critical life support systems. Specialized protocols optimize for the limited bandwidth, high-latency characteristics of the habitat's external connections, employing aggressive compression algorithms and intelligent caching to minimize dependence on real-time surface connectivity. Quantum communication technologies may eventually revolutionize underwater connectivity. Quantum entanglement, what Einstein famously called spooky action at a distance, theoretically allows instantaneous information transfer regardless of intervening medium. While practical quantum communication systems remain in early development stages, they would be particularly valuable in underwater environments where conventional physics imposes severe constraints on classical communication methods. Beyond technical challenges, underwater communication networks must address cybersecurity concerns that exceed those of conventional systems. The isolated nature of underwater habitats makes them particularly vulnerable to communication disruptions, while their critical life support functions make them potential high-value targets. Advanced encryption systems, anomaly detection algorithms, and physically isolated emergency communication channels all contribute to a defense-in-depth security approach necessary for these uniquely vulnerable environments. The economic viability of underwater habitats depends largely on their ability to extract and utilize resources from their surrounding environment. While early facilities may primarily serve research or military purposes, sustainable underwater cities must eventually develop productive economic activities. The ocean offers abundant resources, from minerals and energy to biological compounds and aquaculture opportunities, that underwater habitats are uniquely positioned to access and process. Seawater itself represents the most immediate resource. Beyond providing water for human consumption through desalination, seawater contains dissolved minerals in concentrations that, while dilute, become economically significant when processed at scale. A cubic kilometer of seawater contains approximately 4.5 million tons of dissolved salts, including commercially valuable minerals like magnesium, bromine, and lithium. Traditional extraction methods require substantial energy input, but emerging technologies like selective ion exchange membranes and biomimetic extraction processes promise significantly improved efficiency. Lithium extraction from seawater represents a particularly promising opportunity. Current lithium production primarily relies on environmentally problematic evaporation pond processes in sensitive ecosystems. Seawater contains an estimated 230 billion tons of lithium, thousands of times more than accessible land-based reserves. Recent developments in electrochemical extraction technologies have demonstrated potential for economically viable seawater lithium recovery, potentially revolutionizing supply chains for battery production and energy storage systems critical to the global energy transition. Deep-sea mining offers access to polymetallic nodules, potato-sized mineral concretions containing manganese, nickel, cobalt, copper, and rare earth elements critical for advanced technologies. These nodules, found in concentrations of up to 15 kilograms per square meter in some regions, represent an enormous untapped mineral resource. Current estimates suggest that the Clarion-Clipperton Zone alone, spanning 6 million square kilometers in the Pacific Ocean, contains more nickel, cobalt, and manganese than all land-based reserves combined. Underwater habitats could serve as processing hubs for these resources, potentially reducing the environmental impact compared to surface processing approaches. On-site processing would minimize the volume of material requiring transport to the surface, reducing both energy requirements and ecosystem disruption. Metallurgical processes specifically designed for pressurized underwater environments might achieve efficiencies impossible in conventional atmospheric processing, particularly for pressure-dependent chemical reactions. Biological resources may ultimately prove even more valuable than mineral extraction. Marine organisms have evolved unique biochemical adaptations to survive in extreme conditions of pressure, temperature, and chemical environments. These adaptations produce compounds with potential applications in medicine, materials science, and industrial processes. The pharmaceutical potential alone is staggering. Marine organisms have already yielded breakthrough drugs for cancer treatment, pain management, and antiviral applications. Bioprospecting operations based in underwater habitats could access deep-sea ecosystems with unprecedented efficiency, collecting and analyzing samples while minimizing environmental disruption. Preliminary processing facilities could identify promising compounds before sending concentrated samples to surface laboratories for detailed analysis. This approach would dramatically accelerate the discovery process while reducing the ecological footprint of marine bioprospecting operations. Aquaculture represents another economic opportunity uniquely suited to underwater habitats. Current surface-based fish farming faces significant challenges, including waste management, disease control, and conflict with other marine activities. Deepwater aquaculture systems operated from underwater habitats could access consistent water temperatures, avoid surface storm disruption, and potentially integrate with habitat waste management systems to create closed-loop operations with minimal environmental impact. Energy extraction from methane. Hydrates, ice-like structures containing natural gas found in deep-sea sediments, represents another potential economic activity. Global methane hydrate deposits contain an estimated 2 times more carbon than all other fossil fuel reserves combined. While extraction presents significant technical and environmental challenges, underwater habitats could potentially enable safer and more controlled access to these resources, particularly if combined with carbon capture technologies to minimize greenhouse gas impacts. The sustainable extraction of these resources will require careful integration of economic activity with environmental protection. Underwater habitats could serve as both extraction hubs and environmental monitoring stations, collecting continuous data on surrounding ecosystems to ensure operations remain within sustainable parameters. This dual role might help resolve the tension between resource utilization and conservation that has complicated terrestrial extraction industries throughout human history. The most sophisticated engineering solutions cannot create successful underwater habitats without addressing the human element. The psychological and sociological dimensions of underwater living may ultimately prove more challenging than the physical infrastructure requirements. Creating truly habitable underwater cities requires careful attention to the unique social architecture of subaquatic communities, designing not just physical spaces, but social systems that support human flourishing beneath the waves. The psychological impacts of underwater living begin with the confined nature of these environments. Studies from analogous confined habitats, including submarines, Antarctic research stations, and space missions, consistently identify several key stressors: limited personal space, reduced privacy, restricted movement range, and the omnipresent awareness of a hostile external environment. These stresses can manifest as increased irritability, sleep disturbances, depression, and interpersonal conflicts, collectively termed confinement syndrome by behavioral researchers. Architectural mitigation strategies begin with thoughtful spatial design. Research from the NASA Human Research Program suggests that visual relief, the perception of distance beyond immediate surroundings, significantly reduces confinement stress. Underwater habitat designs increasingly incorporate large viewports, offering expansive ocean vistas and internal spaces with varying ceiling heights and non-parallel walls to create perceptual variety. Advanced lighting systems mimicking natural daylight cycles help maintain circadian rhythms essential for psychological well-being. Beyond physical design, successful underwater communities will require carefully structured social systems. Research from isolated, confined, and extreme ICM environments suggests optimal community sizes, ranging from 50 to 150 individuals, large enough to provide social variety but small enough to maintain community cohesion. Larger underwater settlements would likely adopt modular social structures, organizing inhabitants into interconnected neighborhoods of optimal size while maintaining broader community integration. Occupational diversity represents another critical consideration. Early underwater habitats have typically housed homogeneous populations, predominantly researchers or military personnel with similar backgrounds and objectives. Sustainable underwater cities will require diverse occupational profiles including engineers, healthcare providers, educators, service workers, and administrative personnel. This diversity creates social complexity that, while potentially increasing conflict opportunities, ultimately provides psychological resilience by replicating more natural social environments. Governance systems for underwater habitats present unique challenges. These communities occupy literal islands of habitability within an immediately hostile environment, creating interdependence levels that exceed even the most isolated terrestrial settlements. Traditional governance approaches emphasizing individual rights may require adaptation to prioritize community survival. Several proposed models draw inspiration from maritime law traditions where captains hold significant authority during emergencies while maintaining democratic processes during normal operations. Cultural development within underwater communities may diverge significantly from surface norms. The combination of physical isolation, shared risk, and tightly integrated resource systems naturally encourages cooperative rather than competitive social structures. Historical examples from isolated communities suggest that unique cultural practices, specialized vocabulary, and distinctive art forms will likely emerge relatively quickly in underwater settlements, potentially creating communities with strong internal cohesion but increasing disconnect from surface culture over time. Transgenerational considerations introduce additional complexity. While early underwater habitats will house exclusively adult populations who chose underwater living, eventually children will be born into these environments. These submarine natives will experience underwater environments as their normal context rather than as exotic or challenging surroundings. Educational systems must prepare these children both for life within their underwater communities and for potential integration with surface society. Communication technologies will play crucial roles in preventing underwater community isolation. High-bandwidth connections, enabling rich interaction with surface communities, including immersive virtual reality experiences, can help maintain cultural connections despite physical separation. These technologies allow underwater inhabitants to participate in broader social and cultural exchanges, reducing the psychological impacts of physical isolation while enabling specialized underwater communities to contribute their unique perspectives to global discourse. As we contemplate the development of underwater cities, we must recognize that they represent not just technological achievements, but new forms of human community. The most successful underwater habitats will be those that balance technical requirements with human needs, creating environments where people can not merely survive, but thrive beneath the waves. In this synthesis of engineering precision and human-centered design lies the true challenge and promise of underwater habitation. Not just constructing buildings under the sea, but building communities that may help redefine humanity's relationship with our planet's final frontier.